Well, hello everyone. Today we're going to do the wind load analysis using Portal Method. This video is actually the computer version of the wind load analysis part 3 of 3, so you can see better. So Portal Method has three conditions of the analysis of frames. Number one, a hinge is placed at the center of each girder right here. Since this is assumed to be a point of zero moment. And number two, a hinge is placed at the center of each column, since this is assumed to be the point of zero moment as well. At any given floor level, this number three, the shear at interior column hinges is twice that of the exterior column hinges. So the interior column has twice the shear of the exterior columns. So to solve for shear, we have to cut the column from this point here, the hinges we have, from L, M, and N, and then draw the free body diagram from this cut. So we draw it here. We have free body diagram number one, and then we can solve for shear. The second free body diagram is taken from the first floor column O, P, and Q. We cut it there and then draw the whole frame as a free body diagram number two right here. We draw the free body diagram number two, and we have shear number two here. Shear is represented as V. The wind loads here are the wind loads taken from video number wind load part 2 of 3. That video is dedicated to calculating the wind loads. Okay, and then once we get that, we apply it here to this frame, the transverse frame. We don't worry about the longitudinal frame. I explained that in video wind load 1 part 1 of 3. So transverse frame. This is the wind loads here. And we have all the free body diagram. Now let's solve for V1, the shear one. From free body diagram number 1, solve for B1. B1 here, the equation here. V1 plus 2V1 plus V1 equals to 4B1 is equal to the wind load. Equate that to the wind load. So 8.72. V1 now is equal to 8.72 divided by 4. V1 is 2.18 kilonewton. So we have the V1 there solved. Now let's go for V2. Same thing. Put this in the equation. V2 plus 2V2 plus V2 is equal to the wind loads. This is 8.72 plus 2 wind loads now for this free body diagram. 29.63, add all this together is 38.5. V2 now is 38.35 divided by 4. V2 is 9.59 right here. So we have V1, V2 solved. Now let's go solve for shear. Free body diagram number 3, isolate joint G. We isolate this joint D, we cut that G, we cut that from the free body diagram number 1, and then we can solve all the unknowns here. All the magenta color markings there are the unknowns. The G, JX and JY and LY are the unknowns. So from free body diagram 3, solve for shear. Let's solve for GY first. Solve for GY, we have to take the moment at joint G right here. Summation of moment G is equal to 0. GOI has 3, lever arm 3 is equal to the LX is 2.8, has a lever arm of 2.5. GY now is equal to 5.45 divided by 3. GY is 1.82. When you take a moment at G, right here, axis of rotation, all the forces passing through there is equal to 0. Gx would be 0, wind load becomes 0, Ly becomes 0, and we only have these two forces to solve, alright, which is, and the unknown is Gy. We have one known, which is the V1 Lx. So Gy we found 1.82 kilonewton. Now solving for Jx. To solve for Jx, we have to take the moment at joint L right here. Summation of moment at joint L, Jx has 2.5 lever arm going counterclockwise, and the Gy as well is going counterclockwise, so this should be added, and then equate that to the 8.72 has a lever arm of 2.5 since the axis rotation is right here. So 2.5 Gx equals to 8.72 times 2.5. The Gy now is transposed to the other side of the equation, so we can get the Gx, because these are known values here on the side, the unknown is on one side. So transposing 3 Gy to the other side of the equation becomes negative, so it is minus 3 times 1.82. Solve all this together, we have 16.34 divided by the lever arm of Gx. Gx now is equal to 6.54 right here, kilonewton. So we have two unknowns solved. Now we have to solve the last one, the Ly. Solve for Ly, you have to take the moment at joint G. To take the moment at joint D, Gx is 0, Gy 0, and the wind load is 0. So summation of moment at J is equal to 0. Ly has the lever arm 3 Ly now is equal to only one force there left. It's 2.818 times the lever arm is 2.5. So this is the moment axis of rotation here. So the Lx is 2.18 will rotate clockwise rotation, that's positive, alright. And the Ly will rotate in the counterclockwise rotation, and then it should carry a negative, but we transpose it to the other side of the equation, now becomes 3Ly positive. Alright, so it's a shortcut method. We equate, when the forces is opposing each other, we have to put this in between the equal sign. Alright, the other one is clockwise, and the one is clockwise, the other one is counterclockwise. You have to equate that, put that in between, separating the equal sign. So that's the shortcut method of transposing one member of the equation from one side of the equation to the other side of the equation. And when you transpose one member of the equation from one side to the other side of the equation, the signs should be changed. So that's why 3Ly now becomes positive. So Ly now is equal to 5.45 divided by 3, the lever arm of Ly. Ly is 1.82 kilonewton. So we have all these three forces here solved. Now we gotta make sure that all the values and direction of the force are correct. To do that is to solve is to check your answers using two conditions of equilibrium, one vertical and one horizontal. Let's go for vertical forces. Measure vertical forces. What are vertical forces? The GY and the LY. Okay, so GY going up, positive, and LY going down, negative, is equal to 0. That must be equal to 0. So 1.82 minus 1.82 is equal to 0. 0 on this side is 0, and that equal to 0 that side. Therefore all the forces here, vertical forces, and the direction of the force also are correct. Now check the horizontal forces. Summation of horizontal forces is equal to 0. Gx going to the left. To go to the left, you have to assign your sign convention, okay? And once you assign it, you stick to it, okay? Don't ever change it from the beginning up to the end. So here I choose to the left as positive and to the right as negative. So horizontal forces, Gx to the left gets positive, and the Lx also to the left, positive, and minus, and F1 is going to the right, this negative, F1 is equal to 0. Now Gx plus Lx minus the wind load 8.72 is equal to 0. The adels together is 8.72 minus 8.72 equal to 0. This is 0 now, is equal to 0. So all the forces and direction of the forces we check, and they're all correct. Alright, since all of this checking end up to 0. Alright, so we have all that done. Now let's go to the next joint. The next joint, free body diagram number 4, we have to isolate the next joint, which is D. This half of the column here, half of this column has the LY coming down. The transfer of load, the roles of shear, there are two opposing forces under shear conditions. Since that was the here, the LY is going down, you transfer that load to the next half of the column, it becomes going up. Okay, reverse the sign of the column there. So like the shear symbols here, oh I missed the O here. Shear symbols here, there are two half arrows, one to the left and one to the right. That's the symbol of shearing force. Alright, and then for the beam, one half going up and one half arrow going down. That's when you cut a structural member. This is the symbol, so that's why we have it here. The other half is going down, now the other half, this one is going up. So that's why L1 now is going up, is 1.82 kilonewton. So we have that solved. Always follow the symbols of shears here. Two opposing forces, okay? So at free body diagram number 4, isolate joint D. You have to solve all these unknown. The magenta markings there are the unknown. They are Ry, Oy, and Rx. From free body diagram number 4, solve for shear Ry. You have to do Ry first. This one here. Solve for Ry, you have to take the moment at D. At joint D. When you take moment at D, all forces passing there, this loud becomes 0. I chose that one there. D, Rx becomes 0, Oy becomes 0, Ly becomes 0. All the force that we have left here is the Ox, Ry, and the Lx. Alright, the wind load becomes 0 as well. Anything passing through that axis of rotation where you take the moment about is equal to 0. So mission of moment D is equal to 0. Ry has a lever arm of 3. Okay, and the Ry will rotate counterclockwise. From D, it will rotate counterclockwise, so therefore it has minus 3 Ry. And then the Lx will rotate clockwise rotation, this is positive, and the Ox also is a clockwise rotation. So these two has positive and one negative, and put in an equation equals to 0 following the condition of summation of moments of equilibrium is equal to 0. So to solve for Ry, we have 1, 2, 3 members of the equation here. To solve for Ry, we have to separate Ry from the known values. So we have to transpose Ry to the other side of the equation. But to do that is to change, when you transpose one member of the equation from one side of the equation to the other side of the equation, the sign should be changed. So that's why Ry now has positive, and these two remains in the same position, will remain positive. So we have 3 Ry now is equal to 5 point, we'll work this out altogether. It's a 5.45 plus, I missed the comma here, 28.77. Ry now is equal to 34.22 divided by 3. Ry now is equal to 11.41, and the direction of the force is equal to, is correct. If this is wrong, this will show negative here. Okay, so that's correct. So we have Ry 11.41 now solved. Now let's go for Ry. To solve for Ry, we have to take the moment at joint R, right here. Summation of moment R is equal to 0. There's a lot of forces going on here. The only 0 force here is the Ry and the wind load. All these forces here will rotate around R. So solving for Oy has a lever arm 3, and it's a clockwise rotation. Okay, from R, the Oy will rotate clockwise, so it's positive, and the Lx also will rotate clockwise, so it becomes positive as well, and the Ly will rotate from R, will rotate clockwise as well, so it's all positive, and the Ox also will rotate in a clockwise rotation. They're all positive. Okay, this is the exercise of the sign convention. You cannot make mistake when you use summation of moment and follow your sign convention. You will find out if there's something wrong with the direction of the forces that you assign. Okay, now the first assumption of the Ay here, the white arrow here, is going upward. Okay, so that's why you get positive. Okay, alright, so we'll find out if this is real upward or downward. Okay, so let's solve that. So we have all the equation here. So 3 Oy now is equal to solve for Oy, we have transposed all of these members, known members of the equation, to the other side of the equation. So from the equal to the other side, and the sign, all of this should be changed to, they're all positive, now become all negative. Alright, so 3 Oy will remain in the same position. We transpose these 3, becomes all negative. Now 3 Oy is equal to 2 minus 2.5 times 2.18, the Lx, minus the Ly 1.8, 1.82, lever arm of 3, and minus 9.59. Okay, and this is 9.59 lever arm of 3 as well. So 3 OY now is equal to minus 545 minus 546 minus 28.77. Altogether again has negative, so therefore negative 39.68. OY now is negative 39.68 divided by 3. OY now is equal to minus 13.23. So what happened now? It's a minus sign, meaning the OY minus sign is a counterclockwise right here. Counterclockwise, and it's going down. Alright. So OY, the first assumption we have is going up. It's a clockwise. Now we found, using summation of moment, the actual real sign of and direction of OY is negative. So therefore this OY here, from the moment R axis of rotation, OY will rotate a counterclockwise, which is negative, according to our calculation right here. So therefore sign convention tells us that a counterclockwise also is going down, so negative. Therefore OY is not going up, it is going down right here. This is the correction. OY is minus 13.23 going down. Alright, so that's the beauty of the sign convention. When you stick to it, you will find out the direction of your forces when you solve it through using it all the way, and you find out here there's no magic here. We can find out the direction of the forces. Doesn't matter which direction you put there. When you use summation of moment, you will find out all of them, the directional of all the forces. Alright, so we have OY. We have OY solved, all of them solved now. The RY, OY, now we solve for RX. To solve for RX, we have to take the moment at joint O right here. Summation of moment O is equal to 0. The RX will rotate in counterclockwise, so it has minus RX, and the RY also will rotate counterclockwise. When you take moment at O, right? This is counterclockwise, two of them counterclockwise, and the LX will rotate in a clockwise rotation right here. Rotate like that, clockwise, so it becomes positive. And the wind load also will rotate in a clockwise rotation. So we have all this in the equation here. Minus RX minus 3RY plus 5.5 LX plus 29.63 times 3 is equal to 0. 3RX now. To solve for RX, again, you have to transpose this unknown to the other side of the equation. Therefore it becomes, from negative become positive, and all of this remain the same. Alright, because these are known, so we have to separate the unknown from the known values. So minus 3 times 1141 plus 5.5 times 2.8 plus 29.63 the wind load times 3 the lever arm 3. 3RX now is 34.23 negative plus 11.99 plus 88.89. Work this out together, becomes 66.8 65 divided by 3. Rx now is 22.22 kilonewton, and the direction of force, direction of Rx is correct. Now since we all have the shear forces, they're solved, the unknowns. Since we solve all the unknowns, now we have to check the answers whether it's correct or not. Check the answer again. You have to use summation of vertical forces and summation of all the horizontal forces. Summation of vertical forces here is equal to 0. OY, you found it negative, so minus OY plus RY plus LY is equal to 0. OY 13.23 plus 11.41 plus 1.82 going up, 13.23 plus, if you work this out, this is 13.23 equal to 0, minus 13.23 plus positive 13.23 equals to 0. 0 now is equal to 0. So all these forces, the vertical forces, are correct, including the direction. Now to check the horizontal forces, you have to use the horizontal forces equal to 0. The conditions of equilibrium, horizontal. What are the horizontals? Rx, horizontal, plus OX, they're in the same direction. Okay, it's equal to, and this is the opposing direction now, to the left, to the right, 2963 plus 2.18 right here. Okay, this is one direction and this is the other direction, so I equate that shortcut method of the sign convention. Okay, so we work this out. To work this out is 31.81, and also if you add this up, it's also 31.81. So 31.81 is equal to 31.81. Transposing this to the other side of the equation becomes negative 31.81 minus 31.81 is equal to 0. 0 now is equal to 0. So all these forces here that we solve and including the directions are all correct. So now let's get to the final free body diagram of all the forces to the reaction RA and the moment at C. As you can see here, the transfer of load, the OY here is going downward. Now the transfer of load, half of this column here is right here at the reaction A, right here. Transfer of load now is becoming, OY has become upward, and it's supposed to be positive here. Okay, so it's upward, positive. That's the transfer of load at joint P, right here. Oh, that's joint O, right here. And then the shear OX here is going to the left. This is 9.59, and this time now, following the rules of shear symbols, two opposing forces. When this is to the left, the transfer load becomes to the other half of the column, it becomes to the right. Alright, and also at the half of the column of joint C,
is also going to the right. So the reaction array now is equal to the upward load of 13 kilonewton, and the reaction array is supposed to be positive. I missed the sign there. That has to be changed. This is negative, therefore when you transfer load, this is supposed to be positive.